Okay, good to remind me here. I didn't look at that this is not the recording. I stopped the recording when we went for the break, and I forgot to open that. Okay, good to remind me, Mohammed. Okay, so yeah, so let's come back to that. When we were talking about performance measurement, so the best time is you can measure it through CPU time, right? So when you're talking about CPU time, again, this is something that you people have probably done. So I'm just going to go through that quickly. So when you're talking about CPU time, it's actually how many CPU cycles a program is going to take, and what you do is you multiply that CPU cycles by the clock cycle time, and then you're going to get the CPU time. So for example, if the program takes say 10,000 cycles, and each cycle is of 100 picosecond, you multiply 10,000 100 picosecond, whatever that time comes, that's your CPU time, or the time taken by the program. Okay, so or you can write it in a different way, that instead of cycle time, you can define clock rate. That's the same thing. Okay, so when you're talking about CPU clock cycles for a program, now the CPU clock cycles for a program is a little difficult thing to calculate how many clock cycles the program going to take, right? So one way to do that is to have a figure like CPI, or cycles per instruction. So that's an average figure. So for example, if we say that CPI is say 2.4, and then there are 1,000 instructions. So there are 1,000 instructions in the program, and each instruction, the CPI is cycles per instruction. So each instruction on average is taking 2.4 cycles. So what you're going to do is multiply 1,000 by 2.4, and this is going to give you the clock cycles for a program. So remember, what we were finding was we were trying to find was CPU time, and the formula for CPU time is the clock cycles in a program. Because we know the cycle time, that's going to be something that can be determined from the frequency. So, but this thing is difficult, cycles for a program. So one thing that that can be done is, if you want this figure, you take the instruction count in the whole program and multiply it by CPI, right? If you know the average CPI. But if you don't know the average CPI, you can do this using a formula like this, when you have CPU cycles per program, instruction count, which obviously I'm going to explain how to find the CPI. So, and then if you put that in the top equation, the same thing becomes this. So I'm just going to skip that and move on quickly. So when you're talking about different instructions in a program, they all have different timings. So some instructions are slow, some instructions are fast. So they take different cycles to complete. For example, if there is a load instruction, maybe it's going to access memory, it's going to be slow. But if there is a branch instruction, maybe it's just going to access internal registers and it's going to complete earlier, right? So different instructions have different cycles per instruction. So what we can do is divide our program into different classes of instructions. So what could be the different classes? Say, for example, all the arithmetic instruction can be included in one class. The load instructions could be another class. The stored instructions could be another class. The branch instructions could be another class. So this is how we can separate them into classes, such that each class is going to have a single CPI, right? So say, for example, we have n different types of instructions classes. So what we can do is, and when we know that the CPI of a particular class is same, so what we can do is take the instruction count from the whole program. So for example, there are 5,000 add instructions, 2,000 load store instructions, and say 1,000 branch instructions. So what you can do is take the instruction count and multiply them with their CPI to get the clock cycles, right? So using the expression, we can also express the CPU time. So if you know that what the total cycles are, so what you can do is, I'll just, okay, so what I can do is I'm going to just give you an example of that so that gets clear. So for example, that the add instruction completes in 4 cycles. The load instruction completes in say 10 cycles. The branch instruction, or let's say store instruction, completes in 8 cycles, and say a branch instruction completes in 3 cycles. So these are the different timing of instructions. And if in your program you have got say 5,000 add subtract instructions, okay, say 500, say 100 of load instructions, 70 of store instructions, and say 60 of branch instructions. So that's, if you add all these together, that's your instruction count, the total instruction count. But we are not interested in the total instruction count. We are interested in finding out the CPI. So what is the CPI? So 500 instructions are going to take 4 cycles, and 100 instructions are going to take 10 cycles, and 70 instructions are going to take 8 cycles, and 60 instructions are going to take 3 cycles. So what are you going to do then? You're simply going to multiply this thing. So you're going to multiply these two numbers together, right? And then you're going to add them together, right? So I hope this is clear. So if I need to find out what is the total time my program, what is the total cycles my program is taking, so I know that my program has got 500 add instruction, and each add instruction takes 4 cycles. So I'm just going to multiply 500 by 4, 100 by 10, 70 by 8, and 60 by 3, and get the sum of all of them, right? Is this clear? So that's the same thing that's happening over here. So when we're talking about this formula here, so what we are doing is instruction count of each particular class, multiply it by its particular CPI. So for example, add instruction, there are 500 of add instruction, right? And each add instruction is taking 4 cycles plus, so summation, there are 100 load instruction, and each instruction is taking 10 cycles, right? So if you do all of that, you're going to get a count which is going to give you a total CPU cycles. And if you put that in the previous formula, what you're going to get is the CPU time, or the total time that we want to find out, right? So this is another way to find the CPU time. So this is a better way because it's better than the previous one, because in the previous one what we were doing was we were just using the CPI here, cycles per instruction. Instruction count was totally multiplied by the average CPI, right? We are defining this thing. So how to find that average CPI? So the average CPI can be found out by this formula here. So you can do something like this, where you're going to add up the individual CPI per particular class, and then you add up all this thing to get a CPU clock cycle. So that's the same thing here. And overall CPI can be found out by, so how can you find the overall CPI? So this thing here, you just have to divide it by the instruction count. So if you divide it by the total number of instruction, then you're going to get the average CPI, right? So for example, if I need to find out what is, so this is the CPI of add, this is CPI of load, this is CPI of store, this is CPI of 3. But if I want to find out what is the CPI of my whole program on average, what is each instruction taking, so what I can do is add all these together. So that's going to give me total number of cycles, divide them by this number added together, that's going to give me a total instruction count. So total cycle divided by total instruction count is going to tell me on average how much is one instruction taking, how many cycles is one instruction taking, right? So you can do that yourself as well. So that's going to give you the average CPI. Okay, so let's take another question here. So what I can do is I can end my lecture also over here, because there are many questions here which you can do it yourself as well. So there is nothing difficult here. I'll just go with one of them. I have written all the answers here as well, but let's try to do that ourselves first. So let's try to do that. So consider the execution of object code with 2 million instructions. So that's the total number of instructions that we have on a 2.4 gigahertz single core processor. So we have a single processor, and that's the clock rate, that's the frequency, 2.4 gigahertz. The program consists of 4 major types of instruction as shown below. So we have some arithmetic logic instructions. So they are taking the 1 cycle per instruction, and they are 60% of those instructions. So remember, in the previous case, we were taking a count. Here we have percentages. Okay, so since you are all engineers, it's not difficult for you people to understand this thing. So how to convert the counts into percentages? So it's, if you have percentages, it's actually something like you are dividing it with the total count to get that thing, right? So load store with cache hits, 2 CPIs, and 18% branch has got 4 CPI, and 12% in the whole program. Memory references with cache miss, they can be load stores which are not found in cache. They are going to go to the secondary memory, to the primary memory, or RAM in this case. That would take more CPIs, and there are 10% misses in the whole program. So what is asked is, you have to find out the average CPI when the program is executed on the processor. So you have to calculate the average CPI when the program executed on the processors. How to do that? So yes, can anyone try that? So can anyone try to give me an answer for that? How can we do that? Because I normally ask my student to do that in the class. Yes, anyone? How to calculate the average CPI? We have looked at the formulas for that. We have looked at so what to do? Yes, anyone who can explain me? Take your time. Yes. Akash, Imtiaz, Fahad, Altaf, Saeed Heather.
So the average CPI, we have been given the total number of instructions, and from the percentage we can get the exact number of instructions that are being implemented. For example, 60% of 2 million would be some value, and that would be multiplied by CPI. And then we will add all the instructions to get the average CPI.
Okay, good. So that's simple. So as you have known, but what you really don't need this 2 million as well, because if you are given that 60% of them are taking 1 CPI, so this is actually 0.6 multiplied by 1, right? And then what you can do is 0.18 multiplied by 2, because these are percentages, so they are weighted averages. So what it's already defined in a way. It's like 0.6 and 0.18. So what you had to do in by dividing it, you already have that number over here. So what you need is the percentage of these. So you don't really have to multiply and get that number and then further divide it by 2 million. It's not necessary, because if it's 60% defined here, you just have to multiply 0.6 by 1, 0.18 by 2, 0.12 by 4, and 0.1 by 8. And that number that you're going to get would be the average CPI. You don't have to further divide it by anything, the instruction count, because you're taking the weighted averages, right? Is it okay?
Yes, sir. Done.
Okay, thank you. And then, right. Then we have another question, which is calculate the corresponding millions of instructions per second rate based on the CPI obtained in the above part. So now once you have that number, the CPI, the average CPI, and you want to calculate how much would be the millions of instructions per second. So you have the CPI, that how many cycles on average is one instruction taking. Now you have this, there, how many instructions are there, and what is the time of each cycle, right? So then you can calculate how many millions of instructions are executing per second, right? So I leave that to you. You can do that yourself. I'm sure it's not very difficult. Right. So I'll come to my last topic of this lecture. Now we can improve the performance by different techniques. Like one of them is to go for the common case. When you talk about memory systems, you go for locality of references, right? So when you go for programs in when you write programs in computers, they have the tendency that the data that they access or the instruction that they want are localized. The references are localized. That is, if you have reference one item in memory, it's more likely that you are going to reference the next item which is close to it, right? So that's called as the principle of locality. So it's localized, the references is localized. Sometimes it's also referred to as a 90-10 rule, which is 90% of the time, 10% of the code is running. So 10% of the code is the more frequent code of the program, and it's run about 90% of the time. Okay. So if you can take that 10% of the code in a faster memory, obviously it's going to give you better results, right? So programs are not random. They have a particular order or particular sequence to access data from memory or instruction from memory, and you can take help from that and you can improve your performance using that. So they are both temporal localities and spatial localities. I'm sure you have studied that earlier as well. So just going to go to the next topic. Focus on the common case. So if there are if you are going to build some system and you have two choices to make, you have a trade-off to do. So you are going to always favor the frequent case over the infrequent case, right? So if both of them are taking equal efforts, you are going to go for the frequent case over the infrequent. So what is the frequent case? The frequent case is a case which happens a lot more time. An infrequent case, something which is which does not happen, which happens occasionally, you can say. So what do I mean by that? For example, if you have a choice to improve the performance of say a decoder, the instruction decoder, or improve the performance of a multiplier, so which one would be the frequent case? So when we have two things here, a decoder, instruction decoder would be used for each instruction. So every instruction has to be decoded, right? While if you're talking about a multiplier, so only a multiplication instruction is going to use a multiplier, right? So the frequent case here would be the decoder. So if you're going to improve the performance of the decoder, that's going to give you better benefits than you do for a multiplier, right? So that's one another way of improving performance, that you can go for improving the common case. If you're talking about, then we have another way to find compare performance. We call that as Amdahl's law. So Amdahl's law states that the performance improvement to be gained from using some faster mode of execution is limited by the fraction of time that faster mode can be used. Now, what do we mean by that? So I'll just go through that once more. Performance improvement to be gained from using some faster mode of execution is limited by the fraction of time the faster mode can be used. Okay, so I'll come to that. So when you're talking about Amdahl's law, so what we say is, so this is our original program. So so I'll just a little better. So this is our original program, and it takes some amount of time to execute, right? So this is a timeline. This is a timeline showing that this is the time it takes to from zero to say some number t. So it's going to take some t time to execute. Now what you can do is you thought about improving some part of that program, some maybe hardware or something else, uh, and that part that you have improved takes about this much time. So this is the time that you have improved, right? So this was your original program, and this you tried to improve that program, and once you have improved the program, the time that for that program that you have improved is this much only. Okay, so this means that if you have now a new one, so this time from here to here is going to remain same, because you have not changed that, right? And this that you have improved, it depends upon how much factor that you improved. For example, you have improved it twice. So if it was taking 10 seconds, now it's going to take 5 seconds, right? So if it was taking 10 seconds and your factor improvement is twice, this means that it's now going to take 5 seconds, right? So what is the total improvement? It's obviously not by a factor of 2, because the factor of 2 improvement is only for this portion, not for the remaining portion. So for example, if the remaining portion was 50 seconds, it's still going to be 50 seconds, right? So you have improved something by a factor of 2. So from 60 seconds, it has improved by just 55 seconds, right? So it's not a factor of 2 on the overall program. So I'm going to come back to that statement again. So performance improvement to be gained from using some faster mode of execution, that any improvement that you do is limited by the fraction of time the faster mode can be used. So if it's used only 10 seconds for 10 seconds and you want to improve that 10 seconds, the maximum that you can do is maybe have the whole thing completing in say 0.00 second, but still 50 seconds of work hasn't been improved and it's going to still be there. So if you go for a maximum even improvement, you're going to see if I improve this factor instead of say 2 times, if I make it 10 times, right? If I make it 10 times, and I have improved it by a factor of 10. So now it was taking 10 seconds. Now it's taking just how much? 1 second, right? So it's taking just 1 second now. So from 60 it tends to 51. Again, 60 by 51. How much is that? 60 by 51 is not 10 times. So this means that if you want to improve something, you need to find out what factor is it affecting. So if it's a smaller factor, whatever improvement you do, it's only going to affect that particular amount of time. It cannot affect the whole thing. So it's a very common sense thing, right? So if in the program you are doing some enhancement, that enhancement is limited to the fraction of time that particular thing has been used. So that's the thing which is determined here. So performance improvement to be gained by using some faster mode of execution is limited by a fraction of time that faster mode can be used, right? So normally when we talk about speed up, you talk about comparison of time. So we talk about execution of tasks without enhancement, over execution tab with enhancement where possible. So if you're going to talk about Amdahl's law, we have two terms here, the fraction enhance and the speed up enhance. So when we talk about the fraction enhance, it's actually the fraction of computation time in the original computer that can be converted to take advantage of the enhancement. For example, in this case that I've just discussed, so if the total time was 60 seconds and I'm going to improve this particular fraction, so what is that fraction of the total? So I'm talking about 10 over 60, right? So 10 over 60 is 1 upon 6. So that's the fraction. So I'm just going to affect 1/6 of the program, and 5/6 of the program is going to remain same. So this term is then called as the fraction enhance, or FE. right? Then the other term is speed up enhance, the improvement gained by the enhanced execution mode. So what is the speed up enhance or the factor by which you have enhanced it? So that is the other thing that mentioned over here. What is the factor? So that is the speed up enhance. Now, if you know these two things, then you can easily calculate the overall speed up. Now, overall speed up sometimes represent SP. So you can do that yourself over here. What will that thing be? So if I'm going to just go to a new picture here. So if I say that this is my total thing and this is my fractional enhance. So since it's a fraction, the remaining part would be 1 minus FE, right? Okay. Now, if I'm going to improve something over here by some factor, it's going to reduce that time because fractional is a time. However, this 1 minus FE is not going to be reduced, but the other factor is going to be reduced. And how much is that going to be reduced? By a factor of speed up enhance. So it's going to be reduced by a factor of, so I'm going to have a different division sign here. It's more visible. So that would be fraction enhance over speed up enhance. So this new term would be, this thing would be, but what would this thing would be? This would be the same thing, 1 minus FE. Now, when you talk about fraction speed up, it's the comparison of times. So this is the older time, original PC time, and this is the new PC time, new enhanced time. So when you're going to calculate the speed up, you're comparing their times. So what you get is, what is this? 1 over 1 minus FE plus FE or SE, right? That's the time of the original over the time of the new one, right? So that's easy to do. So what you get is 1 minus FE plus FE over SE. Okay. If you want to find out the speed up, that is 1 over 1 minus FE plus FE over SE. And then there are certain problems over here related to Amdahl's law. I would like you to do that yourself. Try to see what are, so the answers are given over here. So I'm going to stop my lecture right now. So you can go through these questions yourself. Try to see, I'm going to share these slides with you. Okay. And in the end, I'm going to also give you the questions for chapter 1 if you don't have the book. So you try to do whatever questions you can do related to Amdahl's law, related to power, frequency, and DFS, right? So try to do that yourself. Okay. Any question here? So inshallah, we are going to meet the next week. But before we leave, so since we have 1, 2, 3, 4, 5 people over here, now I'm going one by one. Akash.
Yes, sir.
You are probably enrolled in 2 courses. Which when is the other course? At which day is the other course?
Sir, Computer Network Protocol, Monday.
Monday. Okay, so Monday is 1 day. Okay, so Hail Said.
Yes, sir.
So you have 1 class on Thursday. That's my class. What's the other one?
Cyber security.
When is it? When is your other class?
Cyber security, but I shifted from cyber security to computer architecture. I don't know now if I still in 2 courses or only computer architecture.
Okay, so you can sit in 2 courses, but okay, so you don't know which day is that. Okay, Imtiaz sir.
Sir, I have 2 courses. The other one is the AOS, Advanced Operating System, the Tuesday class.
Tuesday. Okay, so Monday and Tuesday both are gone now. Okay, Fahad Khan.
Sir, same Tuesday and Wednesday.
Tuesday, Wednesday.
Sorry, my mistake. Tuesday and Thursday. Your
Okay.
class.
Thank you. So still Wednesday is left. Okay, Sayyid Altaf Ali.
Monday and Thursday.
Monday and Thursday. Okay, good. So this seems that we have got Wednesday and Friday. Okay, so what I was asking was, since we have one class missed, so now what would be the appropriate time for you people? Is 6 to 9 okay for you? Because normally for masters we had 6 to 9, but now it's online classes. So I just want to discuss it with you. Is 6 to 9 okay with you?
Yes, sir. Okay for me.
Okay. And if I take some class, is it okay if I take it on Saturday, Sundays, or is it okay if I have to take it on some weekday?
So it should be on, I think, Sunday or weekday. Saturday, there are some other things to do.
No, if I, for example, take an extra class, for example, we missed the last week's class. So should I take it on Wednesday, or do you think that maybe for job you don't have time for? Uh,
So Wednesday after 6 इसी तरह से जैसे आज क्लास हुई है तो ऐसे फिजिबल हो
Okay.
जाएगा.
Okay, so that's good. That's good. So no, I'm not going to take it next week, but maybe for later. I've just asked you people to give your suggestions. So maybe later, some other week, I'm going to arrange 2 classes. Okay. Okay. So okay. Thank you all. Right. Thank you for. I'm going to stop it here. Yeah. Is there any question?
Sir, will you be uploading this presentation?
Yes, I would be. So the good thing here in Google Suite is you have got 3-4 tools. One of them is Google Meet, where we are discussing. The other one is your Drive. The other one is your Classroom. So all of that would be loaded in your Classroom as well. So if there are any assignments or quizzes, I'll give that in the Classroom. So check the stream of Classroom. You can have a mobile app for that as well, or you can check it on PC whenever you want. Mobile app is better because it gives notifications whenever new material is uploaded. So for me, I'm going to give the meeting code one day earlier. So it's actually the same code of our class, but maybe I'm going to change it. Every week, or maybe it's the same, but I'm going to post that post every week, when is our next class going to happen, right? And that's going to be Thursday, but I'm going to post it one day earlier than that. So Wednesday I'm going to post the link for that, and then you can click that link. And in that same classroom, I'm going to post the material for that. So I'm going to post the chapter number 1 as well, and also the slides. And the videos, the recording is automatically going to be shared with you in your drives.
Okay, sir. Sir, sorry to interrupt, but battery मेरी 1% हो गई है.
Oh, thank you. Okay.
Light अभी तक नहीं है.
Okay, thank you.
Okay, sir. Allah Hafiz. Thank you.
Okay, thank you. Allah Hafiz.